Many students can feel intimidated by stoichiometry in the way that a dimensional form of writing the problem can seem long and cumbersome. But let's compare the dimensional approach with the stepwise approach. So we have a problem here with a single replacement reaction of wanting to see how many grams of lead as a solid precipitate would be formed if we put 6.72 grams of aluminum in an excess of lead nitrate aqueous solution. Here's our balanced equation right here. So the tendency of many students who are used to a particular method or steps will try to at first figure out how to memorize a stepwise form of solving problems like this. And so the most logical way of solving this problem is in a series of 3 steps, and that is under the assumption that we first have recognized that our known being grams and our unknown being grams and our known being grams, that, well, yes, we are going to need 3 steps. Here we would need to convert our grams to moles, as we know that grams cannot be meshed with molar relationships directly. We have to divide by the molar mass and convert our known aluminum into moles. Then we are able to multiply by the mole ratio. This essentially gives us the amount of lead precipitate that would be formed as a mole amount. But we would have to know that since the symbol for what's being asked for is in grams, we will need to add a 3rd step, which is where we convert the products to grams by multiplying the product by its molar mass. On the other hand, the dimensional approach, being so much more visual, allows us to not quite have to think so much. As I've said in earlier videos, the mole ratio of unknown over known is really the main pattern that you need to know, because all stoichiometric calculations involve taking the relationship from the balanced equation, because that's all that stoichiometry is rebalancing this equation for a set amount that you have to work with. From there, we can visually inspect our known value. We see that it's in grams. Is it possible to dimensionally cancel it with the denominator here in the mole fraction? No, that's a dead giveaway. Hey, we need to convert something to moles. So we know that if we divide by the molar mass, we can do that. Also, we know that we don't have to memorize whether we multiply or divide so much as can we set this up so that these values cancel. And they do, and we have things now in moles. Then on the other side, we see that if this answer is requested in grams and we stopped at this step, that wouldn't work because that gives it to us in moles. By making this a gram value by multiplying by the molar mass, we can solve the problem. And if you just wanted to simply memorize this 3-step way of doing it, that's fine, but we're always going to make a mistake, and that's why looking at it dimensionally to see what values cancel helps us keep straight whether it was logical to multiply our known by the molar mass, which would be wrong, or divide it, or to multiply our unknown by its molar mass, which is correct, or divide it, which would be wrong, or whether the unknown should be on top or the known should be on top. So the dimensional method, while looking cumbersome, really takes no more time than the stepwise version does, and by arranging it in this visual one-shot approach, we can look and see the relationships that are going on here between the values of moles of aluminum, moles of lead, grams of aluminum, and verify whether we've arranged our problem correctly. In the long term, we're not having to really quite think so much, and we have a means of checking our work visually. So give the dimensional approach a shot if you're thinking that the stepwise approach is the most logical way to go. In the end, as long as you show your work, that is acceptable. But over long term, as you take physics and other science and math courses, eventually the dimensional approach will have to be worked into your framework for solving problems to be able to get into more advanced levels of study.